Okay. Okay. So we have Dr. Frank who sorry, yeah, Peng. So he goes by name Frank. He's I think you are still the most recent faculty joining our department.
Last year.
Nobody has joined yet this year, right? So yeah, I think he's quite likely the latest faculty to join us, and he works on very exciting new area, really very upcoming area. There's a lot of excitement about it. People felt that we need to have faculty in quantum computing and related area. So it's a great area for you all to learn about in case you're early in your research and explore that. So thank you for coming, Frank, and let's get started.
All right, good afternoon, everyone. Yeah, I'm Frank Fu. I'm assistant professor here at UofSC. So today I'm going to talk about programming quantum computer with types, but mostly it will be something about quantum computing 101, and I will show you some programs about how to build quantum circuits, and please feel free to interrupt me if you have any question in the middle of my talk. It's all fine. So, well, first, general question is why quantum programming languages? Well, for me, the answer is pretty straightforward because I do research in quantum programming languages. But for you all, I would like to also mention that the reason that people are interested in quantum computing is that there has been research that show quantum algorithms can offer a substantial speed up for certain computing tasks, such as factoring integer, which is very important in the areas of cryptography, and also simulating Hamiltonian, which play an important role in simulation or physical or chemical simulation. So there are tasks like that quantum computing are shown theoretically can offer speed up, right? So that's why people are interested in doing research in quantum computing and even building actual quantum computer. So yeah, so in fact, there are some big companies are building quantum computers right now. Two of the main players in the field are Google and IBM. Yeah, so people actually are trying to build quantum computer. That's the point. Right. So then back to quantum programming language and programming quantum computers, right? So how do we program a quantum computer? Well, currently, the most common way to program a quantum computer is by building a quantum circuit or building quantum circuits, and then we send the quantum circuits to the actual quantum computer, and then the actual quantum computer will run the circuit, so to speak. So we will see a little bit of quantum circuits later in the talk. And then the reason I mentioned quantum circuit is that when people describe their quantum algorithm, it's usually described in terms of the language of quantum circuit. So they draw circuit diagram and so on. But we want to program those circuits, right? So that's why we need a programming language for doing that. And then the last thing about that is fairly unique to quantum computing is that debugging quantum algorithm can be more expensive than debugging a conventional program. One reason is that, right, because when we program in languages like Python or C or Java, if we want to debug, we most likely do some kind of print statement, right? We print the value of this variable in your program, you see what's going on. But for quantum algorithm, we don't really have printing the state, so to speak. We cannot really print out the value of certain variable in quantum algorithm. The reason is that because physics, that the physicist says that when we are looking at a qubit, so qubit is like a variable, if you will, for now. If you look at it, it will change the state. So that's really weird, right? When you look at something, that thing changed, right? So that's a very intuitive or informal explanation of why we cannot just do a print statement to look at the to debug a quantum algorithm. So that means that we have to use other means to debug our program, right? So one way to do that would be something like we build a simulator of some sort. We run our algorithm at a small scale in a simulator, or we can make our language that is so expressive that it make it harder to write wrong program, right? So that's probably a bit of a subtle point, right? So it's really like a distinction between writing a program in Python versus writing a program in, say, Java, right? So if you have a type error in Java, most likely you cannot compile your program, whereas in Python, you only know the error when you run your program, right? Whereas in Java, Java have to type check your program before compiling it. So that's so in this talk, I will be talking about a language that is based on a notion of typing or type checking. So we want to have types so that we write more correct program to begin with, rather than spend more time to debug our program. Okay, so that's a bit of a motivation about why I am interested in quantum programming languages. Okay, so now I want to also briefly mention what kind of research I do. So mostly I build tools to facilitate programming quantum computers. So that means that I design high-level programming language for programming quantum circuits. And I am also interested in verifying quantum program, right? So when we have a program, how are we going to make sure that this program is doing what it's supposed to do? That's actually an important topic, broadly speaking, but I'm also interested in particular in the areas of quantum computing and quantum circuits. How are we going to make sure that this circuit does the right thing, so to speak? And I'm also interested in compiling from a high-level quantum programming language down to actual quantum computer. Okay, so that's my research in 3 sentences. All right, so next, I would like to give one slide or maybe a couple slides of quantum computing 101. So conventionally, in computer science, we are mostly working with bit information, right? We work with 0 and 1, and everything can be expressed as 0 and 1 essentially, right? So we are familiar with bits. So the only thing that you might not be familiar with is this notation, right? This is called cat notation, K-E-T, cat notation. But for now, you can just think of the cat is some kind of funny brackets around the actual 0 and 1 that you are familiar with. Okay, so that's bit. And then with quantum computing, we are more interested in a notion called qubit, right? So what is a qubit? Well, qubit is actually a linear combination of 0 and 1, right? So this alpha and beta, they are actually complex numbers, and they are the squares of them add up to 1. So so intuitively, a qubit is it's not exactly like a bit, right? A bit can only be 0 or 1. There's nothing in between. But a qubit, on the other hand, might be actually be something in between 0 and 1. And the coefficient here, alpha and the beta, they are sort of indicating the probability of this qubit being in the 0 stage or versus the probability of this qubit being in the 1 stage if we are measuring the qubit. So when I say measuring the qubit, it's sort of like observing the stage of the qubit. It will sort of collapse the qubit into 0 or 1 with alpha squares of probability, the qubit will be in the 0 stage. With beta squares probability, a qubit will be in the 1 stage, right? This only happens when we are measuring the qubit. If we are not measuring the qubit will just stay the same. Okay, so we'll talk about measurement in a moment. But any questions about qubit? Does this make sense? All right. Yeah, I see.
So are the information for the computer stored as a qubit instead of memory?
Yes. So qubit is like the basic units of how we store information in quantum computing.
You said like qubit represent a probability of being in zero value. So if we are trying to retrieve information that is stored as a qubit, how are we sure like we are retrieving the same information?
Right. So in practice, people sort of tune their algorithm in a way that they make this beta really, or the absolute value of this beta really close to 1, so that they know once they measure it, they know for sure they will get, for example, the 1 value. But in general, we don't necessarily know whether we are getting 0 or 1. But there are ways that you can program the qubit in a way that give you a deterministic result. So I think.
Maybe before could you explain what it means if the qubit state changing when you're looking at it or measuring it?
Right.
That's one.
Yeah.
And the second is, so the concept of qubit and bit is just like in math where we have complex numbers and real numbers, right? So is it right for us to draw parallels between those two?
Well, for bits, we don't really need to deal with any real number nor complex number. For bit, we just work with 0 and 1.
Yeah.
Whereas in qubit, we do need to work with complex numbers.
So for example, here, if our alpha was 1 and beta was 0, that would just represent the bit 0.
Yeah.
And if alpha was 0 and beta was 1, that would represent the bit 1.
Yeah. So in a sense that qubit is a generalization of bit.
Is it necessary that alpha plus beta equals 1 or?
Yeah, for physical reason, it's like an axiom that in order to be a qubit, your qubit must have to satisfy this condition. This is also for the probability reason that when you measure a single qubit, the probability of getting 0 and 1, they should add up to 1.
So alpha square plus beta square, much more real and square. So
right, because alpha and beta themselves, they are just complex number, right? We want the absolute value, we want to get a real number from a complex number. That's one standard way to get a real value from a complex number. Great. Yeah, one more.
So when you're writing
good question. We don't really translate unless we are simulating quantum computing. In which case, we are, by saying simulating, I mean, we are using conventional computer to pretend to be like a quantum computer. Then in that case, we might have to worry about that. But when people are building actual quantum computer, we don't really translate it back to conventional. All right, great. So that's qubit, right? Now, but that's just one qubit, right? Just like when we are working with classical computing, we are not just working with one bit, right? We work with multiple bits. So in quantum computing, we are also working with actually multiple qubits, right? So the way we represent multiple qubits is by this funny symbol called tensor products of two qubits. But for now, we don't really need to worry about what the tensor product actually means. But when I write this symbol, it just means a two qubit state, right? So what are two qubit states? Well, they are of this form, right? So a two qubit state phi, again, is a linear combination of four different things, right? 0, 0, 0, 1, 1, 0, and 1, 1. Whereas all the coefficients here, they are the squares of them, they also add up to 1. Okay. So just like when we are working with 2-bit information, right? We have 4 possibilities. Whereas when we are working with 2 qubit, we are working with linear combinations of 4 possibilities. And then this go on up to finitely many number, right? So for example, 3 qubit, you are really working with linear combination of 8 different things and so on and so forth. Okay, so that's qubit and multiple qubits.
What does it mean for the quantum computer to enforce this sum of all the coefficients square to 1?
Right. So that's really up to the hardware provider when they say this register represent a qubit. That means that as a producers of this hardware, they guarantee that this qubit is a genuine qubit, meaning that the amplitude, by amplitude, I mean this coefficient, they actually have to add up to 1. Otherwise, there's no guarantee, right? Of course, there are experiments to make sure that it's actually the qubit rather than some random stuff.
Yeah, but if you cannot provide that, then this whole mathematics breaks down, right?
Yeah. You do need this. Yeah. Wait. So we have qubits, right? But having qubits alone is not enough to do computation. Just like conventional computing, we have bits, but we also need something to update the bit. So in quantum computing, one way to update a qubit is by performing the so-called unitary operations, right? So what is unitary operations? Well, they are linear operations, right? For example, in the case of 1 qubit unitary operation, they are sort of like function that take a qubit and turn it into another qubit, or update this qubit to a different state, right? So that's what we mean by unitary operation, roughly speaking. But it's a linear operation, meaning that when we apply this unitary operation U over a qubit that is in this state, right? We can distribute it over this sum, right? So that's what we mean by this unitary operation is linear. So unitary operation, not only it's a linear operation, but it also satisfies this property. Okay, so what does this mean? This means that so this U dagger means the reverse of this unitary operation, right? So it means that unitary operation has this special property that is actually in some sense reversible. So if you apply this unitary operation to a qubit, this qubit change to a different state. But the funny thing is that you can unapply this, or you can undo this operation so that you can turn this qubit in the new state back to its original state. Right, so this notation means that, for example, here we first perform the U operation, then we perform the inverse of the U operation, then that corresponds to doing nothing to a qubit. And similarly, if we do the inverse of the U first and then we perform U, then again, we still do nothing to the original qubit. Okay, so that's some, so in some sense, this is called reversible because it has this going back and forth, or you can turn the state back to its original state. So that's unitary operation. Yeah, I see a hand raise.
So if I have like a string which I have sent through a hash function, and then there is a hash text, would I be able to bring back using this?
Well, we already know that, wait, is hashing reversible?
Not a normal case.
Yeah, right. So yeah. So when we have an unreversible function, that is not unitary by definition. So yeah, so we might not be able to directly do that. Maybe there are some indirect way to somehow achieve part of the goal, but I'm not too sure. But in order for an operation to be called unitary, it has to be reversible. So that's like a definition, right? Yeah. Any other question? Okay, so that's like a abstract definition of unitary operation, right? But now let me give you some example of unitary operation. And in fact, they are actually called content gate, right? So gates is like a unitary operation. So one of the most common one is the negation, right? So here we use the symbol X for negation for historical reason. So when X applied to the 0 state, we get 1, and 1 we get 0, right? So because unitary operation is linear, that means that it's enough for us to know how the operation acts on 0 and 1, right? Because when a qubit is a linear combination of 0 and 1, we can just distribute the operation to each of the 0 and 1 states and just apply this definition. Okay. So as we can see, this NOT gate, of course, is reversible, right? If we apply the NOT gates again, we get back to the original state. So that's NOT gates, and then we have couples of more interesting gates that you might not seen before. For example, we have this gate called C-NOT gate, where the C means control. It's like control NOT gate. So what does that mean? Well, if we say this is the first bit, this is the second bit, it means that when the first bit is 0, we do nothing to the second bit, right? So 0, if C0 apply to a 2-qubit state that is already in the 0, 0, then it does nothing. Or if the 2-qubit state is 0, 1, then again, it does nothing. But when the first bit is 1, then it negates the second bit, right? So we say the first bit is the control bit, the second bit is the target bit. When the control bit is 1, we perform negation to the target bit, right? So when we have 1, 0, then the second bit gets flipped. And similarly, when we have 1, 1, the second bit also gets flipped. So note that this C-NOT gate is like a 2-qubit unitary operation. It acts on a 2-qubit state rather than 1-qubit state. Whereas the NOT gate it's a single qubit operation, so it works on 1-qubit state. Okay. Any question about C-NOT? Yes.
So not just about C-NOT, but for unitary operations in general, is there a process of finding the inverse of the operation?
Yes, yes. So I guess as a in-class exercise, can you tell me how do you inverse the C-NOT?
Flip it. So if the first unit is 1, then you keep it same, and if it's 0, then you flip it.
Right. So this C-NOT is exactly almost like the NOR gate, almost, right? So it's cell inverse. So if you apply the same operation again, you get back to the same state. Great. Yeah, so of course we know that any 2-qubit is actually a linear combination of 4 states, right? So when we apply the CNOTs to a 2-qubit in general, we have to distribute this CNOT over all the 0 and 1. Okay, so that's CNOTs. Then we have 2 more and a few other more interesting gates. So one of the other is called Hadamard gate. So what it does is that when we apply it to the 0 state, we get a qubit that is in this form, right? It's 1 over square root of 2 multiplied with 0 plus 1. So what this means is that, so this qubit, right, because the square of 1 over square root of 2 is 1 over 2. So essentially, it's like it turns a 0 state into a 0 or 1, half and half. If you measure this qubit, there are 50-50, you get 0 or 1. So it's sort of like generating some kind of coin flip operation. But of course, when we have 1, we still have this 1 over square root of 2, but rather than plus, we have minus. So observationally, these two are not really that different, but this minus sign actually play a role in some other settings. So it's still important that the sign is still important. But yeah, that's essentially what Hadamard gate does. It sort of generate a coin flip from 0 or 1, essentially. Any question about Hadamard gate? Yeah, it's already became a little strange, right? So now we are going to be looking at something that is even more strange. So then we have this gate called phase gate. So what it does is that if our qubit is in the 0 state, it does nothing. But when it's in 1 state, it also does nothing to the 1 state. But it multiplies with the complex numbers here. Right, this complex number is something like e to the I theta, right? So it's a complex number in the unit circle, on the unit circle, so to speak. So these 2 gates or operation are really like what made quantum computing strange. They begin to make things very strange, and people start to do computation using complex number, which is not something that we normally do in computer science. But yeah, so that's the 2 new things. Yes.
On that, doesn't the bit already have an alpha beta probability associated with it? So what does that gate do to that probability?
It will not change that, right? Just like, let's say our qubit is alpha 0 plus beta 1, right? The way we apply Hadamard is that when we apply Hadamard to that qubit, we will get alpha h applied to 0 plus beta h applied to 1, and then you do the algebra to add them together.
So it modifies those alpha beta for the qubit.
You don't, it doesn't modify the alpha and beta, but it modifies the 0 and 1 in that 1 qubit. All right. Okay.
But
Yeah.
we only have 0 and 1.
Well, here, when we give the definition of the unitary operation, is enough to know how it works on 0 and 1. Once we know that, we know how it works for a linear combination of 0 and 1, right? We just distribute this. That's why when I describe this unitary or quantum gates, I only describe them by saying how they act on 0 and 1. But in practice, they actually act on a linear combination of them. Okay. So, well, I guess fun fact, Hadamard sort of is also like X gate, it's also self-inverse, right? So if you apply Hadamard to 0, you get a qubit that is in 0 and 1. But if you do the calculation, if you apply the Hadamard again, you will flip it back to the 0, right? That's really strange. So I invite you to do this exercise after the class. But for phase gates, the inverse is actually the reverse of the phase theta is the negative theta, right? Because that sort of cancel out this e to the I theta. Okay, so all these are reversible in a mathematical sense. All right, so that's the mathematical definition, right? Now I want to give you a slightly more high-level description of those gates. So in fact, it's actually more convenient to just write diagram for those operations. For example, for the X gate or any kind of single qubit gate, we write it inside the box, and then we have wire coming from left to right. So the diagram is left to right, right? So we have a single qubit coming in and a single qubit coming out. And we can even give a type to those operations. So what do I mean by type? By type, I mean, for example, X has the type qubit to qubit. That means that it's a function that inputs a qubit and outputs a qubit, okay? And similarly, C0 is a 2-qubit operation. So it takes the tensor products of qubits and return the tensor products of qubits. And this is the notation for C0. This circle thing denotes the NOT operation, whereas the black dot there denotes the control bit. That means that when the first wire is 1, then we fire the second, well, we apply the NOT gate to the second qubit. And otherwise we do nothing, okay? And then Hadamard, we have the circuit notation for the Hadamard and the phase gate. So that's the circuit notation and the types for those operations. So in practice, we often assume those operations are given to us. They are like the operation that the quantum computer says it can perform. And then we just use it as a primitive, right? Just like when we are doing arithmetic, when we assume addition and multiplication is given, for example. Okay, so any question about diagram? Yes.
So not about diagram, but if we talk about binary bits 0 and 1, so in hardware side, we see that high voltage is represented as 1, and low voltage, like nothing, is represented as 0. But here we are dealing with the values between 0 and 1. So how the quantum circuits gets that value in like physical mean, like what is the voltage? Is it the voltage current or?
I see.
How-
Yeah. That's a very good question. And unfortunately, I don't know the answer to that. It's really up to the implementer of the quantum hardware to make sure that certain operation, it's very low level thing that we probably don't need to know as a programmer. Just like when we are writing program, we don't necessarily know how the bit gets flipped, right? So we sort of assume it's given, but it's still a good question. Well, it's actually a hard question to answer, because people actually need to come up with different kind of strategy to implement the qubit and the unitary operation. But unfortunately, I'm not an expert in that area.
I have a question about the phase unitary operation. So when it's 1, it's e to the I theta, right? So that means that it just takes the 1 qubit and moves it to some theta angle on the unit circle. Is that how?
Well, that's the meaning of the e to the I theta. The theta corresponds to the angle in the unit circle of the complex plane. So we for now we can think of this as just a number multiplied to the 1 state.
So basically, when we have a qubit of the form alpha 0 plus beta, beta 1,
Mhm.
basically
Right.
applying phase gate to that would just mean that the beta coefficient gets.
Yeah,
multiplied.
yeah, get multiplied by this complex number. Yeah, so that's how you sort of adjust the alpha and the beta somehow, right? Good question, thanks. Any other questions? Great. So, well, I'll show you three more common gates, just for fun, right? So we have some other more strange gates like Z gate, which again does nothing to the zero. When we have one, we apply the negation. So again, Z gate is also self-inverse. If you apply it twice, you get back the same thing. And we have S gate, which also does nothing to the zero, but apply an I to the one. So, and we have, well, of course, these three are actually instants of the phase gates when the theta angle is pi, and this is pi over 2, this is pi over 4, essentially. But we have this sort of identity, right? So if we apply the T gate twice, it's the S gate. If we apply the S gate twice, we get the Z gate. And we also have this kind of relationship that, for example, an X gate can be represented by first performing an Hadamard, then followed by a Z gate, then followed by an H gate that will give you an X gate. So we have this kind of identity between those quantum gates. So there are some relationship between them that might be helpful to understand them. Okay, so so that's unitary operation, right? So other than unitary operations, we also have other kind of operations like measurement, for example. So measurement is differ from unitary operation in that measurement is not reversible. It's sort of like a destruction of a qubit, so to speak. So that's why the type of the measurement is qubit to bit. Okay. And specifically, what it does is that when we apply the measurement to, for example, this qubit, alpha 0 plus beta 1, we get the state 0 with certain probability or 1 with beta squared probability. And there's no way to go back to the original qubit anymore. Okay. So that's measurement. So we also have some notation for convenience, right? So like in quantum circuit, you often see notations like this. We have a 0 here and then a wire going out. So that's a way to express we are initializing a qubit that is in the 0 state. So this unit is just like a dummy. Well, it's a type that has a single value. So it's a way to turn preparing a qubit in the 0 state into a function. So it's for technical reason we put a unit here, but it's really like preparing a particular qubit in the 0 state. And dually, we have a termination. So it has a wire coming in and nothing coming out. So it's like saying this qubit has to be in the 0 state. So the type for the termination, so term for qubit termination, is qubit to unit. So it consumes the qubit and then, yeah, it sort of express the fact that it just consumed the qubit and there's nothing coming out. So that's like a termination symbol. But intuitively, this just means that this is saying that this input wire, the qubit that is represented by this wire is in the 0 state, and that's it. Whereas the initialization is saying that this output wire, this output wire that represents the qubit is in the 0 state. Okay, so that's initialization and termination. So we can think of it as initializing a variable, if you will. And this termination, you can think of it as sort of garbage collects a qubit, if you will. Okay. Now we can look at some program, right? So So this is a program that is written in a language called Proto-Creeper. It's like a small experimental language I developed, but hopefully it will give you a good sense of what it does, right? For example, let's look at the type of this val00 function, right? So let's ignore the exclamation mark for the moment. That's for generating, so that's saying that this function can be turned into a quantum circuit. That's this exclamation mark says, okay? But it has the type unit to, so this unit to qubit star qubit. The star is for the tensor product. So so this val00, what it really, just from the type, we can see, well, it input nothing. The unit is representing nothing, and it output 2 qubit. So it means that this val00 function, all it does is it's preparing a 2 qubit state. Okay. So what does it actually do? Well, it first initializes a qubit and called it A, and then it initializes another qubit and called it B. And then we apply the Hadamard gates to the first qubit, just like here, right? And then we apply the CNOT gate using the second bit as control. So the CNOT here, this is the control bit, this is the target bit. So this program sort of is representing this circuit, right? So it make 2 initialization, apply the Hadamard to one of the qubit, and then it apply the CNOT gates to the 2 qubits here. Does it make sense? Does this part of the program make sense? Okay, so then because that function has that exclamation mark, we can turn it into a circuit that has input unit and output 2 qubit. And once the operation of turning a function into a circuit in this language is called boxing. So it's like boxing the function into a circuit. So once we box the function into a circuit, then we can print the circuit to look at a circuit that corresponds to that program. Okay. So that's this function. Question? Make sense? Yeah, so this part is just saying that if we have a function from S, if we have a function that looks like exclamation mark S to S prime, then we can box this kind of function into a circuit that has input type S and output type S prime. So there are certain things I want to mention, right? So for example, let's look at this program. It's also called val00 function, but here, rather than writing the variable A here, I write B and B here, right? So it's a common mistake, right? Sometimes we just make a typo because we want to write A, but we accidentally type B, right? And then when we want to compile our program in this language, we will get an error, right? In Python, you probably will not get an error, right? You only discovered it once you run your program or test your program 100 times, then you discover there's an error somewhere.
Why this is wrong? Like,
Right.
even with like if we initialize just 1 qubit and apply 2 different operations on that and then combine it to form qubit with 2 set of qubit, then it should work. But like, why this?
Right. So it's a good question. Yeah, that's exactly what I am getting at, which is that, so qubit, unlike is very strange in the sense or not strange in the sense that qubit is like a resource, right? Meaning that we do not really have the power to copy or make a clone of a qubit and turn it into 2 qubit, right? So single qubit as dollars, right? If you have $1, can you make $2 out of $1? You cannot, right? So so qubit is like that. It's a kind of resource. So the fact that we are using this variable b twice, in a sense, it's almost like we somehow managed to copy this qubit and make 2 qubit, right? So that's actually not allowed. That's a property of quantum computing. So in this particular language, we make it a typing error. We can detect this kind of error at compile time, right? When we try to compile our program, we cannot even compile our program because our program has this kind of error, right? So this sort of allow us to spend more time to understand our program rather than spending more time to debug our program, arguably. Right? So in this language, that's why this is a typing error. Okay, so this is the error message, but it's essentially saying the variable b is used twice, and that's not allowed. Okay. Any question about this?
The last slide, it says it has type qubit. I don't understand how it.
Oh, yeah, the variable b has type qubit, right? Because b is coming from, so by the way, this open and close parenthesis is the value for the unit. So unit has only one value, is this open and close parenthesis. So this b equal init 0 apply to this unit thing. As it means that we are preparing a qubit that is in the 0 state, right? Sort of like we are initializing a variable that has the value 0, kind of like that, except we cannot make 2 copies of this variable, right? So that's the different thing between program in this language versus program in C or C++ or Python for that matter. Okay.
I'm sorry, I still didn't get how we got to the type qubit.
Because init has the type unit to qubit, right? And this open and close parenthesis has the type unit. So if we supply the unit value to the function, we get the qubit value. Right? Just like if we have a function from integer to Boolean, if we call this function on 1, right, then the expression will have type Boolean. Yeah. So because of that, because b is applying this init function to this unit value, b has the type qubit. So we are really using b as if it's a qubit that is in the 0 state. Any other questions? Great. Okay, so why do I mention this bell 00, or what does it actually mean, right? So I want to briefly tell you what it's actually doing. So we already saw how we can generate this circuit by writing the program for it. But mathematically, what it's actually doing is the following. Right, when we perform the initialization of 00, we start with a 00 state, right? Then we apply the Hadamard gate to the first qubit. Right, 00 is a shorthand for 0 tensor 0. So these two are the same. We apply a Hadamard gate to the first qubit. Therefore, this 0 becomes a coin flip. And then tensor 0, right? Because the second qubit, there's nothing here. So we have a coin flip qubit tensor the qubit that is in the 0 state. Then we can do some algebra, right? To simplify this expression by distribute this inside here, we get something like this, which is 1 over square root of 2 with a 00 state and 10 state. Okay. And then we apply the CNOR gate using the first bit as control, the second as target. So therefore, it does nothing here, but it flips the second bit here. So finally, we get this 1 over square root of 2, 00 plus 1, 1. Does this process make sense? Questions? Okay, so this state is called Bell 00 state. Because it's actually a very interesting 2-qubit state. Why it is interesting? Well, the first thing is that it's a typical example of 2-qubit that is sort of entangled with each other. So it's a way to generate an entangled 2-qubit state. Because this 2-qubit state cannot be written as a tensor product of two separate qubits. Right, you can prove this as an exercise, but there isn't any single qubit states phi 1 and phi 2 such that when you tensor them, you get this particular state. You cannot separate them in some sense. So if we think of tensor product as separating two qubit states into two separate qubits, we cannot actually do that. So that's one strange thing about this state. And maybe another thing about this state is that when we measure the 2-qubit state, again, we have 50% probability of getting both 0 and both 1. So in some sense, the state of one already determines the state of the other, right? For example, when you measure this, after this operation, when you measure the 2-qubit, they are not independent anymore. They are related to each other. So that's why it's called entangled. These 2-qubit entangle with each other. Okay. Question? Yes.
That mean it eliminates the possibility of the 0, 1,
Yeah.
0.
Yeah, you can never get 1, 0 or 0, 1. That's another, yeah.
So why in diagram we have two outputs?
Right, the two output here means 2-qubit state. Yeah, it means 2-qubit state rather than two separate qubit. Yeah, so a 2-qubit state is different from two separate qubit that we make them together. Of course, initially we start with this 0 tensor 0, right? So they are actually separable. They're just 0 and 0, right? But after the computation, they are entangled with each other. They're related to each other.
We don't have a symbol for entangled qubit.
We don't have a symbol for that, right? The tensor product are for separate qubit. We combine them into 2 qubit, right? But once they entangle, we cannot easily. Yeah, there's no way to separate them. Yeah. Okay, that's the, yeah.
So, if it's just an example for the 0, 0 state, and what happens if you apply Bell 0 to it, or can we try it out with 0, 0, 0, 1, 1, 0, 1?
Yeah, good point. By that you mean this, right?
Yes.
We can, so this is just the case for 0, 0, right? So the Bell 0, 0, the 2 0 there is corresponding to the 2 0 here. Of course, you can initialize 2 qubit that is in the 1 state, or 1 in 0 and 1 in 1 state. But they all give rise to the same phenomenon, namely that you start with separated 2 qubit that are sort of separated with each other. But after this Hadamard and the CNOR, they all become entangled with each other. So for example, beta 01, beta 11, they are all inseparable, or they're all entangled state.
So, at the end of it, after performing the operation for some other qubit, say 0, 1, would we also get a value like, it's like a 50-50 chance?
Yeah,
between,
yeah. But
say 0, 1, 1, 0.
Yeah,
or
yeah.
something like that?
Yeah, you do the same computation, right? Except you start with some 0, 1 or 1, 1.
Yeah, but it would lead to the same result.
Yeah, it would lead to 1 over square root of 2, but here you might have something else.
Yes.
Good. So when do we stop? Did anyone know when is the right? I mean, when do I have to stop? Did anyone know?
The class ends at 3:10.
Oh, 3:10. Okay, so it's already okay. Well, I hope you learned something. Yeah. Oh, by the way, yeah, lastly, yeah, I prepared too much, but if you want to learn more about quantum computing or my research, I just want to advertise that next semester I'm teaching quantum programming languages, so feel free to sign up for that. And this semester I teach this semester I'm teaching functional programming, but currently there's also another class called quantum computer science, which you can also learn more about quantum computing. And yeah, please feel free to contact me if you are interested in my research. All right, thank you.
Okay, so, hang on if you don't have to leave. I'd like to meet the people who came more than 5 minutes later and don't have this. Can you bring up the stages? So, we have few slots and I wanted to.
Could you tell me
Get
the
your
timing
thoughts on,
of your ongoing
the
class
topics you
for
are
quantum computer
interested in
science?
to hear about.